Hello and welcome back to yet another episode in CSC 263, Database Management Systems at Adelphi University. Today we continue our discussion about modeling, and specifically we'll start talking about data modeling. This is captured in chapter 10 of the book, so I can speak. Okay, so in the previous episode we introduced modeling as a method to describe the relevant aspects of a complex system. And then specifically we talked about conceptual modeling, which does so in a technology agnostic way. The whole point of creating those conceptual models is to create something that we can understand the system better. So to enhance understanding would be analysis of the system, but also to give us a tool that we can communicate about the system in a fairly unambiguous way. And once we can do that, once we can understand and communicate, we can start designing a system and create hopefully a new or a better system as a result of it. What I should also have mentioned explicitly in the last video is that unfortunately, modeling is not an exact science. It's as much an art as a science. So there's going to be a whole lot of situations in which you have to make judgment calls, and we have to figure out how to deal with those. So in practice, what we'll see is once we're experienced with creating these formal models and fairly extensive models, which we'll do in class, the practice is that you'll often whip something together very quickly in order to double check your understanding and maybe to communicate with someone, but you cannot do that until you have developed that solid understanding of what models look like. So in this video we'll talk about data models, and before we can do that we have to acknowledge that there are typically two distinct perspectives on data. The first perspective is data in motion. As we create information systems, data moves around that information system. It may be presented to a user in a screen, and then it may be processed somewhere in a back-end system to make sure that, I don't know, let's say the tickets are still available. Then the database might go to the update. So there's all these different places where that data is used and where it is processed. And we want to make sure that we know exactly where the data is moving and what is being done with it, but also where it sits in between use, and that is called data at rest. Once we know where the data sits when it is not being used, so for that persistence that we get from a database, we have to figure out how that data is formatted. What does it look like? What attributes does that data have? How can I describe that data, the structural components of the data, which is the data at rest? And those are the two different perspectives on data. Data in motion, which cares about how it's used, and data at rest, which cares about structural properties of that data. Now we want to create models for those, and of course those models have to represent the system in as much realism as possible. And let's go take a look at it. So our first modeling technique is called dataflow diagrams. It's an older mechanism. It's not, for example, a method that is contained in the popular UML, the Universal Markup Language, but I think it's still a very useful modeling technique. It's fairly simple. There's only 4 primitive concepts that we can use to create our models. The first one is the terminal. The terminal is that point where our system connects to the world around it. So when I talked about system theory, where I said every system is contained in another system, that's where these terminals come into play. At all of these connection points is where we'll recognize these terminals. And of course we label these terminals in a meaningful way. The second primitive is a oval. It is a process. And in terms of data and data in motion, basically the way that we consider a process is something that makes data move. And data can only move when it's moved by a process. And that's an important one to keep in mind. Data cannot spontaneously move around. It needs a process to do that. A process is also an action. And so when we label our processes, we say there is a noun and a verb. So for example, we have we do something with courses, what do? We create them. So we create a course. We may check a roster. We may print a transcript. Whatever it may be that we're doing, you typically find these verb-noun combinations to meaningfully label these processes. And I already mentioned a process moves data, which means that it needs to have data coming in and data going out. And data in the data flow diagram is represented by an arrow, specifically a line with an arrowhead on one end. And the arrow is representative of data in motion. That is the data, so we want to describe the nature of that data. In the slide, the diagram, for example, we recognize the student terminal in the top left, which provides a preferred class to a process called register for class. So that is data. Now keep in mind that in the data flow diagram, we move data around. So what is the predominant flow of data? It is not a control flow. It does not specify what happens first and what happens second. It does not indicate who takes the initiative to make the data flow. It only represents the fact that there is data flowing from the student to the process. And then lastly, we have the two parallel lines with a label in between, and that represents data at rest. That basically means, well, the data is not being used in my system. That's where it sits. And again, think of it as a data repository. Do not think of it as a database. A database is a technical implementation detail, and we don't want to have to deal with those at the conceptual level. We think of them as a data store or a data repository, and each type of data gets its own repository. So for example, in this here, I have two repositories. One in which I describe courses and one in which I describe course registrations. I don't go into detail what exactly a course looks like and what a course registration looks like. I just say courses live here. Now, of course, in order for me to put data in my data store, I need a process, just like I need a process to take data out of my data store. Data stores also cannot miraculously produce data, so you have to put in what you're going to take out. But also, if you're going to put stuff in, you will have to take it out at some point because nothing has infinite storage capability. And so there's a couple of rules that we have to keep in mind when we talk about data flow modeling. The first one is that data flows must connect to at least one process. That makes sense because the process makes the data flow, and therefore any data flow needs to be connected to a process, at least in one location. Black holes are data stores or processes that spontaneously create data without that data ever having gone in. We do not allow those. Sorry, wrong way around. A black hole takes in data and doesn't do anything with it, or it doesn't produce any output. Not allowed. What I said first, the thing that spontaneously creates data, that's called a miracle. Also not allowed. And really between these three rules, we have the main key constraints of data flow modeling. Now, we can start putting together our narrative and capture it. But again, we have to make sure that we label everything, because just a picture is not good enough. We want to know what it is that we are modeling. Once we've done this a couple times, and again, we'll do that in class to get your hands on experience, you'll find that it becomes easier to do each time you do it. To make things even more confusing, we're going to have to do this in groups of students, because modeling for yourself is one thing, but modeling with someone else is a completely different story. So we'll see how that goes. After playing around with data flow diagrams, we have a basic understanding of what our system will look like and what its behavior is, who's interacting with it, etc. Now we can start going and look in more detail at these data stores and say, okay, what does this data look like that we have stored there? The data at rest. And that we use entity relationship modeling for. Again, it's a very well-known technique. It is an older technique, but it's still a very effective one. It is a top-down approach. So we start at a high level, and if it turns out that we have too much abstraction, we'll go refine our concepts a little bit more. Stepwise refinement. So what we're going to do is try and identify data that represents things that have an independent existence. So for example, a student has an independent existence. A course has an independent existence. An ID number does not. A name does not. A name without being tied to someone or something is non-existent. So what we want to do is first identify what are those entities, those things that could have independent existence. And then we want to see how they are related. So for example, I may have a student entity and I may have a course entity. How do those two relate? Do they relate in the first place? And if they relate, that's called a relationship. What is that relationship? How do I label that? I can also start identifying properties or attributes of these entities and of those relationships. For example, I might say a student registers for a course, and I can put a registration date on that registration relationship. And so I can start building my model. Entities can only connect to each other through relationships. So they cannot connect directly. There's no direct association between two entities. There's two different commonly used notations that we see. The first one on top is the more traditional notation. You don't see it all that often anymore though. But quickly, a diamond represents a relationship. An entity is represented by a rectangle, and an oval or a circle represents an attribute. So in this, for example, I might say that I have two entities that related through a relationship. Now, more commonly on the bottom, which is inspired on class diagrams from the UML, we'll see a more modern notation where the entity is listed as a rectangle with within that rectangle a section for the different attributes. An entity relationship diagram in this particular case has also these numbers in it. So for example, we see entity and then we see the number 1 going to the relationship. But the relationship has 1 ... star going back into the entity. What this means is called the cardinality or the ordinality. In this case, each entity is part of the relationship exactly once. We'll give a more clear example in a second. But let's first define these terms. The degree of a relationship describes the number of entities associated with it. So let me flip back. The relationship on the bottom has 2 entities, therefore it is a relationship of degree 2 or a binary relationship. We like binary relationships. When we see multiple higher level degrees, ternary relationships, etc., down the road we want to get rid of those. They don't fit very nicely in our relational model, but if we recognize them at this stage, at conceptual modeling, that's fine. We'll deal with them. The cardinality of the relationship describes how often an instance of one entity can happen. So for example, I might say a student can take many courses, or a course can be taken by many students. That's a many-to-many relationship. We are not terribly smart as we are computer scientists, so our counting goes 0, 1, many. That's about as far as we can go. The other aspect is the ordinality, if there is a minimum number of occurrences that something needs to happen. For example, we might say, well, a course section without registrations is useless, so each section needs to have at least 1 student in it, but at most maybe 20 or so. So those are basic terms. In class, we'll play more with these models, and we do some analysis on these models before we start creating our own. But these are the basic terms for data modeling, which consists of data at rest and data in motion. Data in motion is represented by data flow diagrams, which consists of terminals, of processes, of data flows, and of data stores. And data at rest is represented by these entity relationship diagrams, which contain entities, things that represent things in the real world that have an independent existence, attributes of those entities which do not have an independent existence, and the relationship that exists between those entities. that's it for now. Let's go play with this hands-on in class.